Welcome to the short course on how to teach science and engineering. In this lesson 5, I'll give you a sample lecture in engineering and tell you the steps you should follow to make your engineering teaching effective. My name is Sinha, Dr. Ranbir Sinha. I work for Sinha Research, Switzerland. Teaching science and engineering is different from teaching literature, for example. I'll include some points. If you're planning to teach online, I'll include some points about that too. Preparation. You need to prepare for about 30 hours for 1 hour lecture. Okay? First, divide the course into topics. Select the right topics. It's really important. You cannot teach everything that's written in the textbook, which may be 1,000 pages long. Select only the most important topics, most interesting topics. Leave the rest to the students. Okay? Choose appropriate resources. Thousands and thousands of materials, resources on the net. You cannot teach all of them. Most of them are not very useful. Teach the basics, the fundamentals, the concepts, the applications, something that's interesting to them. Okay? Tools. Choose correct tools. Experiments, for example. Select a few videos or animations. Students normally like to see videos, animations, or even real hardware. If you are planning to teach, for example, something electronics, take a piece of hardware. Show the application, and then teach the theory. I always talk about product first and theory later. That makes the students interested. They know ahead of time where it's going to be used, whatever they are going to learn today. Okay? It's important. You may bring some simplified props for your lectures. So selection of right topics, resources, tools, video, animation, very important. If possible, hardware. Sometimes for large machines, for example, a turbo machinery, you cannot bring the hardware. Bring the video animation before you start teaching about something like, say, flow through turbine blades. Okay? Learn the existing online teaching systems. If you are planning to teach online, learn the correct resources that you can use properly to make your teaching effective. For example, I'm using very simple tools. Today, I'm using PowerPoint slideshow. You can use something else. OBS Studio for video recording, just a webcam. Okay, this is important. Master those tools. Just select 1 or 2 basic tools. That's it. The contents are much more important than selection of tools, but use at least 1 tool. Learn it very well. Imagine you are planning to teach 1 average student. If you are teaching online, even during a lecture class, as if you are a private tutor for an average student. Focus on average student. Try to make them excellent. Try to make them understand all the concepts and how to apply them. Okay? All right. Contents, preparation of contents. That's very important. Contents are much more important than tools. I'll tell you right away. Make 2 versions of your contents. For example, the first version should be for you. Details, notes, write down the objective. That's very important. For example, I told you what my objective of this class is today. Lesson 5, I'm going to give you a sample lecture on engineering and also explain to the teachers who are learning from my video what steps they need to follow. Clear objective. You can modify it after you have finished the entire contents. Okay. First, start with outline. Fill the details with text, whatever you're planning to mention in the class or online teaching. Fill the details. Add some pictures. Pictures seem to be more effective than just writing a lot of text, but some pictures, etc. Following my earlier lessons, I have 4 other videos. Go through them, please, and pick up the most important points, implement them. This version is for you. This is detailed notes for yourself. Then make a shorter version. Throw out all the unnecessary things, not so important text, and make a shorter version that you are going to present. For example, I have a lot of details about all these things that I'm talking about in my other notes. I've gone over that many times. I'm showing you a simplified version here. Okay, make a shorter version that will be presented online or even in regular lecture class. Follow the instructions and suggestions given in earlier lessons. You should go through all my videos, please. Thank you. Rehearse a few times, maybe 2-3 times rehearse, record it and see if your flow is all right. Flow should build up, right? Information should build up from something the students already know and then slowly build it up to more and more complex concepts, etc. Okay, flow of information has to be right. Timing, you should not overshoot the time. I recorded this 3 times and I know I'm overshooting the time, so I'm cutting it down today. And improve on the contents of version 2. What are you going to present? I have too much material here. I'll tell you right away. This class is for the teachers, what I'm teaching right now. So I'll include a lot more details than what you are going to present to the students. You have to prepare that. Okay. Version 2, this part, and finalize it. So that's it. Now practice a few more times. Maybe about 5, 6, or 10 times you should practice, okay? Because when you go there, you have only one chance and you have to do it right. Implement, do the online teaching finally, and record it. Your first lecture may not be all that great. There are maybe points where you can improve. You evaluate yourself and get the feedback from the students. Take the most important points. Well, first assess yourself. You're the best judge. If you watch your own video, you'll know. There I could have said things earlier, maybe clarify better, maybe throw in some example. You improve. And feedback from the students, you may get hundreds of feedback. Take only the most important ones, most important and most useful criticisms, and try to improve on those. Here is something from Albert Einstein. Perfection of means and confusion of goals seem, in my opinion, to characterize our age. We use too fancy tools sometimes, very fancy tools, but our contents are not very good. We don't even know what we are trying to achieve. They look very nice, but it's got very little impact on the student. Okay? So do not focus too much on the tools, focus on the goal, please. Now I'm going to go over a sample lecture in engineering, how to teach engineering. Pick up the most important points, implement in your lecture. We are going to talk about engineering vibrations. So first thing to do is, if you're going to teach about vibration, tell them what is vibration, why study it. That's very important. Why study it? If you don't study it, what can happen? So let me begin with something very simple. Please watch this video. This is about flutter. That's a bridge, Tacoma Bridge. A gentle breeze could swing it, could make it vibrate like this. The bridge collapsed. It's a relatively new bridge. This is wind tunnel test by NASA. Airplane wing model. Fighter jet. This is airflow over an airfoil. This is the model. This is a real glider. This is a rocket model. This is an airplane model. And wind tunnel. This is the model of the tailplane. It's a real plane. This is becoming unstable. This plane. Okay. So what did you see? Show a video that excites the students, then they become interested in learning. What you saw is a bridge, almost new bridge, designed perfectly, fell apart because of vibration. That's vibration, okay? Aircraft can break off, rockets can break, buildings can break, okay, because of vibrations. It's a major problem in engineering. You should understand it. Only then you can solve it. Solve the problem, I mean. Okay, so introduction. What is vibration? Why study it? What is the use of learning these things? Example. Something good can be done using vibration. For example, musical instruments. They work on the principle of vibrations. If you want to create wonderful musical instruments, you need to know about vibrations. Headphones. For example, this headphone. There's electrical signal coming there, and there's a little diaphragm here that moves, that vibrates, and that produces sound that I can hear and enjoy. Okay? Microphones, exactly the opposite. Whatever I'm saying, that vibrates the diaphragm, that gets converted into electrical signal, and then you can process the signal using electronics. You can amplify it, for example, make it louder. You can make it sound smoother, remove the noise, all kinds of processing. It's all vibrations, okay? Vibrating sieve, if you want to separate small particles from big particles, for example, big stones and small stones, you want to separate them. Or if in chemical industries, bigger particles, smaller particles, if you want to separate them, food industries, you can use vibrating sieve. It'll be nice to show a video of that too, so people know where vibration is useful for us. And how about the problems? Vibration can be a big problem if you don't know how to control it. Cars, when cars travel, you hear noise, right? It's uncomfortable for the passengers. Also, car going on rough road can shake quite a bit. That's vibration. Trains, details you'll explain later. For now, give them the idea that everywhere there seems to be vibration. It could be useful, it could be a problem. Unless you understand it, you cannot make use of it. Trains, it could be noisy. Sometimes trains can shake so much it can go off the track and can cause accidents. Planes, you have already seen, vibration is a big problem. Noise, vibration, all that. Bridges, you saw that. Even if you make the bridge very strong, it does not guarantee that vibration will not be a problem. It will not break. You have to understand vibration, study this topic very well to solve that problem. Okay? Machines vibrate. Machines that are moving, they vibrate, right? Car engine, for example, or any manufacturing machine. Robots, for example, suppose you have a robot that's supposed to put electronic pieces of electronics on a circuit board. Suppose you are creating a motherboard. If you don't study the vibration of the robot arm, how it behaves, this is what will happen. It will put the wrong pieces in the wrong places. And your entire manufacturing will go waste. The board will not function. Do you understand? So vibrations are extremely important. So what kind of problems vibration can create? Noise, poor performance, or even failures. So now you know how important this topic is. So please take it seriously. This is how you have to convince the students in the beginning, through a video, through some evidences and general knowledge about where it's going to be used, so that they take it seriously. Approach of the study, you have to explain to that. How are you going to study? What are you going to study? So we'll study with something using a very simple problem, very simple phenomenon called simple harmonic motion. You may have to explain these terms later on. What is harmonic? What is simple? Why is it called simple harmonic? Okay. We'll take a very simple problem to explain to start the topic of vibration. Simple mass spring that you have seen many times in physics books also. If possible, bring a piece of hardware, a spring and a mass. Just hang it from a rigid frame somewhere and demonstrate what it does. That's much better than showing just the video. I don't have a piece of hardware, but you can find it from the physics lab or make one by a spring. So take a piece of mass, draw on the blackboard. That's possible too. Okay, real experiment is always better. So here I have a mass hanging from a spring, and this hanging from a rigid platforms. Okay, so I take the mass, hang it to the spring, and put my hand there and gradually lower it. It stops at a point, and then I release it. Stays there. Now what I'll do is I'll ask the students a question. You have to do the same. If I pull the spring from here, pull the mass from here about, say, 5 centimeters, and then release it, what will happen? Let them imagine. Most of them will get the idea. Most of them will give the correct answer. Give them time to think. Always make them think a little bit ahead. Most of the students will say, well, it'll vibrate, or it'll shake, it'll go up and down. Some different words, but basically they are talking about vibration. Concepts are more important. Pull the mass, release it, and show it. What will happen? And this is what will happen. Okay? You have pulled it, released it, and shaking up and down. Very good. That's vibration. That's the simplest thing. It's called mass spring system. Why study that? Very soon we'll talk about it. But these are the steps you got to follow in your lecture. Make sure you have these kind of things. What do we want to study? What do we want to find out? We observed, but what do we want to find out? We want to find out the motion of this. Which parameters does it depend on? Okay. Motion of this basically means its position with respect to time. That's motion, right? Change of position with time. So position with respect to time, that will be our idea. Once we get that, you can always find velocity, acceleration, everything else. All right. Formulate the problem. Okay. These are the basic steps you must follow in almost every lecture. Formulate the problem, introduce the technical terms, their meanings. You can introduce, give simple explanations, not only just define and leave it. They should understand those technical terms, the meaning of them. Okay, that's more important than the definition. Definition can be done later. Explain the approach and how and derive the formula. So as I said, the approach of the study, you have to tell how are we going to solve this problem. That you have to first explain, then derive the formulas. Use physical thinking, drawing, and mathematics, all three together, because you're teaching engineering, not only mathematics. Mathematics is a nice tool, powerful tool to derive these formulas and come up with some equations. That's fine. The concepts have to be explained physically, okay? Drawing definitely helps. Just talking in the air like that is not going to help. Draw the pictures, okay? Let the students calculate the frequency, period, etc., and plot them. Let the students do some work in the class. When you derive the formula, ask them to calculate something, okay? That makes it absolutely clear in their mind, and they get used to these numbers. Finally, in engineering, it's not only formulas, also the real correct numbers, units, all these things are important. All right. Do an experiment and show that the formula works. What I mean is, if you did bring a real hardware, take a video of that one. Okay, if it's shaking, take the video. Once they calculate the actual numbers, frequency, period, etc., and that matches with the video, They'll be very excited. Do an experiment and show that the formulas work. Okay. Experiment. You can make some variations if you have extra time. Vary the amplitude, mass, use 2 springs in parallel series, etc. Put some of these things in the lab class. Lab classes must match what you are teaching in the lecture classes. All right. And see how these things vary. Now, all these things will become absolutely clear in their mind. So when they become engineered, when they see a phenomena, they know that they have seen something similar. They know what's causing it. They can solve it. Okay? All right. It's not only just to pass the course. It's to build the concepts, the ideas, and the dependencies. For example, they should know that somehow through these classes that if I want to increase the frequency of that, I should increase the stiffness of the spring. Maybe add one more spring here. Not in series. They should know. It'll make it softer. I'm telling you ahead of time. We'll show that later. Okay? Or reduce the mass to increase the frequency of that. Ask the students to derive the formula for velocity and maximum velocity from the position formula that you calculate. Don't do everything for them. Don't spoon feed them. Do part of it, introduce the concept and the approach, do part of the derivation, ask them to go into the details and derive more. Okay? Give hints about approximations, damping, etc. What approximations are you making? I'm ignoring the mass of the spring. Okay? These things do affect to some extent. But overall, modeling, you have to explain that. You cannot model every little details, every particle of this in order to solve this problem. It's much easier if you know the stiffness of the spring. If you know the mass, you should be able to calculate it almost correctly. Model is good enough for engineering purposes. Damping, I'm ignoring air damping here. In the next class, or maybe 2 lectures later, you will introduce damping. But they should know there is something called damping. When they see the experiment, it will become clear. So what do you see? This is continuously moving, but in the real experiment, after some time stopped. What stopped it? Let them think about it. Do not tell them the answer. All right. You'll be surprised. They come up with amazing ideas, amazing explanations. Vibration, oscillation, simple harmonic motion, periodic motion, all kinds of terms are involved here. Are there differences? Explain to them. A pendulum swinging is oscillation, but it's not vibration, is it? They should know what to use where. Periodic motion, a motion that just repeats. It doesn't have to be a vibration. Okay, how is vibration different from vibration? Could be simple harmonic motion in special cases like this. Are there differences? They should use correct terms in future. So they should know the differences. They are related, similar, but probably not exactly the same. And vibration doesn't have to be necessarily simple harmonic motion. This is a special case. They should know. Periodic motion. Can you tell me? You are teachers. Can you tell me? Is there periodic motion which is not vibration? As I said, yes. Motion of pendulum or anything that repeats. Periodic motion. That's not vibration, is it? Okay, cause of vibration. They should understand finally that vibration, this mechanical vibration, is caused by, of course, some external disturbance, some force or displacement is given to the system. Also, an elastic restoring force that's proportional to the displacement and opposite in direction. They should understand that part. Okay, just because something is going through periodic motion, they should not jump into conclusion as vibration. They should know that this is what's going to cause vibration of a system. All right, demo, a sample class in engineering. Now I'm going to teach about how to teach, okay, the details. All right, demo with a real experiment, if possible, okay. Take a video of that one. For example, this is an animation, but you could take the video of this mass and spring that you brought and did the experiment in the class, okay. Take the video. From the video, you can always find out how much time it took by playing it slowly and stopping, pausing the video. Cell phone camera. This is a great tool for studying a lot of things in engineering. Take a video of anything that's happening that you're teaching, okay? Later you can study in details. I can count, I can find out how much time it took to make 10 such up and down motion, okay? From there I can find time period and frequency. And at the end of the class we'll try to show that in theory we can calculate, using theory we can calculate, and it matches with this experiment. Take a video. All right, now next step will be draw a simplified diagram. Okay, so this is the mass and spring. Okay, this is this part. The symbol is for rigid support, okay, fixed support, and this is the spring simplified diagram. This is the body. Okay, after I slowly bring it down, and where it stops I just release it, it's not going to fall anymore, so that's where I'll take that one as reference. You could choose any point of this body as reference, that's fine, but I'll choose that position, the neutral position, equilibrium position, as my reference, and I'll call it x equals 0. I'll choose the direction x positive this way from that position. Okay, all right, objective, we want to find out position and velocity of the body as a function of time. When I pull it down and release it, it moves. We want to find that out. Okay, that's called study of motion. Anything that's moving, you want to find its position with respect to time, and once you have done that, you can find velocity, acceleration, etc. And that's the objective. They should know, what are we trying to study in vibration? That's what we are trying to study. Okay, approach, we can write down the equations of motion. Tell them we can write down the equation of motion and solve for position as a function of time. That's what we are going to do. So study of anything that's moving, we write down the equation of motion, try to solve it for position with respect to time. That's a general approach they should do in any problem involving motion. Derive free body diagram. I drew, what I did is, suppose I pull it down here. Then I study only the body, because I'm going to study the motion of that body. This is what you need to do. You need to write all the forces on that. Okay, this is my equilibrium position. I pulled it down, and now there is a spring force. Spring is trying to pull it up there, and that force I represented with F. So I have a body, and there's a force acting on it. At any position, there's a force acting on it. All right, I have pulled it by X amount X. All right, the reference and equilibrium I already explained. This is where the mass stopped dropping when I gradually released it. At that point, all the forces equalized. That means there was a weight, mass times acceleration due to gravity. That's the weight acting there, and the spring force balanced. From there on, we'll ignore the gravity, because that's neutralized now with some constant force. Okay, one can get into the details of that later on. For now, we are not studying that part. Okay. So this is free body diagram, a body with all the forces represented on it. Axis system is very important. Remember, this X I have chosen downwards. Suppose the body is at a distance X from there, from the neutral position. Neutral is equilibrium position. How much is the net force of a spring? Spring force is force times distance or displacement, F times K times X. K is the spring constant. Okay, and with a negative sign, that's the force of the spring. Why negative? I've chosen X as positive this way. I have given X positive displacement, and force happens to be upwards, opposite. That's why I had to put a minus sign. Spring always exerts a force opposite to the displacement. Caution, very careful with X and F. These things in the beginning, the first few classes, engineering students must know they cannot make a mistake in the sign and the axis system. These things are very important. They cannot say, oh, it's only plus minus problem. Entire problem will be wrong. Okay. Newton's second law of motion we have to use. Why? Because if we are studying motion, if you know the force, you know the mass, you know the acceleration, and that's how you start. Very simple. So force equals mass times acceleration. That's Newton's second law of motion. Acceleration is second derivative of displacement. First derivative gives with respect to time. First derivative gives the velocity, second derivative gives the acceleration. Mass times acceleration. That's Newton's second law of motion. That's all I'm doing. There's a representation, shorthand representation for d squared x dt squared, second derivative of x, with two dots. First dot gives the first derivative, dx by dt. Second, the two dots give d squared x dt squared. Okay? If they don't know calculus, it's going to be hard, but I'm assuming you have taught them some calculus. Mass times acceleration. Just a shorthand symbol for that. Dot represents time derivative. So we just flip it and say mass times acceleration equals force, and force I have seen spring forces here, minus kx. Minus k is the spring constant, which is spring force caused by unit displacement. Okay? The spring, if you pull it, you measure the force, you measure the displacement, force divided by displacement. That's per unit displacement, how much force is caused by this. And we are assuming this linear spring. Okay. All right, so this formula is valid. Equals, so that's equivalent to, I bring the mass over there, minus k over m times x. So now this one is funny. The second derivative of the displacement depends on the displacement. Okay, this is very important, extremely important. Acceleration depends on the displacement because the property of the spring. And this is just a constant, negative sign. All right, this is second order differential equation. This is second derivative involved. Okay, this is just the variable itself, x displacement. This is the second derivative of the displacement. And there's a relationship between them. So this second order differential equation. So what do we want to find? We have seen that. We want to find the position. We want to find x as a function of time. Here what we have is the time derivative, second derivative of x, and relates to x. From that, we need to find a formula for x. Okay? A simplified formula for x. So now think, what kind of function will solve this equation? If I choose some kind of function, x, displacement, with time, as a function of time, that will satisfy this equation. Okay, that's what we need to find. Now think about it. How was the motion of this one? Take two approaches, one physics and mathematics. Okay, physics approach will be, they have seen the motion, it was going up and down. So what that means is it has to be a function of time that also goes up and down with time. Okay? What function can go up and down? It could be something like this, right? This function is also going up and down with respect to time. Sometimes positive, sometimes negative, sometimes positive, sometimes negative. This is what it's doing with respect to time. But is that the correct function? Could that be? What does that function mean? It linearly moves with time. Constant velocity, then flips it. Constant, flip. Is that how it's moving? What did they observe in the motion? Ask them. Ask them. One or two of these students said, no, sir, it was slowing down and then reversing, again slowing down, then increasing the speed, then slowing down. What that means is this kind of sharp corners will not be allowed. That's probably not the solution, so it will be somewhat smoother. What kind of function do you think it is? Some of the students will say, I think it's going to be a sine function, a cosine function. Now that's the answer. We'll prove it later. This is smoother. Okay, let them think that what can be wrong. We assume that it's going to go up and down, which should show some sawtooth-like function, and there's something not correct about that. Then the next step, they get most likely sine function is better. Let's try it. Okay. Also, you can derive the formula how to derive, but I'm giving you the solution right away. X a sine omega t plus phi. This is a general solution that will satisfy this equation. Okay, it's a sine function of time. If you wrote just sine t, yes, that would be correct, but then the time period will be fixed to 2 pi, right? Every 2 pi entire cycle, all the angle, again the sine cosine functions repeat, right? So we need to multiply that t with some omega. That will also satisfy this. And this omega, one can find out, it's actually from mathematics, you can find out it's going to turn out to be k over m. You can derive it if you like. Okay, square root of k over m, this constant part. Okay, that will satisfy. Even if I add a constant to this argument, that will also satisfy this equation. Okay, so that's also acceptable. If I multiply that by a constant, that will also satisfy. So it's a general solution. Any function of this form will satisfy this equation. Okay? How this is derived, k over m equals omega, square root k over m equals omega, etc. You can derive the equation and show. We'll talk about this frequency, etc. later on. Okay? Check by substituting if the differential equation is satisfied. I just said this is going to satisfy it. Does it satisfy? Well, this is how it is. How are you going to verify? Just take the second derivative, put it on this side, and put this x over there just from this formula, and see if both sides are equal. This side is going to be a times k over m. This omega comes out because you're taking the derivative of sine. It becomes cosine, and you take one more time derivative because second derivative, that gives you cosine's derivative is minus sine. So minus sine that, and omega comes out twice, omega squared. Omega squared is k over m, right? Okay, on the right side, what do you get? Minus k over m times x is given a sine omega t plus phi. Phi is also called phi, okay? So phi probably is correct in Greek. It's a Greek letter, phi or phi. All right, good. So both sides are exactly equal. So that means this solution is satisfying that. So it's a solution. Are there some other solutions? We'll talk about it later. Okay, now let's go back to this. This omega is called circular frequency. Okay? It's called circular frequency. Let them think about this. That's omega. When it becomes 2 pi, what happens? Not 2 pi, sorry. The entire thing becomes 2 pi. All right, good. Think about those things. And this is called frequency. This is in radian per second. This is called frequency, cycle per second. What that gives is, in 1 second, how many times it's going up, down, up, down, up. Okay, like entire cycle. You start, suppose it starts from 0, it goes to this point. That's 1 cycle. In 1 second, how many cycles it's going to make? Inverse of that, time period, inverse of that basically is how much time does it take to complete 1 cycle from here. If suppose start with 0, 0, up, down, back to 0. Or you can calculate from here, from there, from up, down, then back to up. That's 1 time period. How much time it's taking. Time is plotted on this axis, right? How much time it's taking. That's called time period. If it is making n cycles per second, 1 over n will become the time period. That's the time it will take for 1 cycle. These are very simple things. Okay, check by substituting if the differential equation we showed that it works. Okay, now that's a general form. Here we don't know, we know omega, that's square root of k over m. If we know the stiffness of that and mass, we know that one. That's fine. We don't know phi, we don't know a. These two constants, excuse me, they depend on the initial condition, how did you start to make it vibrate? Okay, so let's take some initial conditions, and that will give me a particular solution to a particular problem. At t0, that is when I left it, that time there was a displacement I had given, which is a, but I just released it without giving it a velocity. It started with 0 velocity. That's one condition. That will give you a set of a and v. Ask them to find out. Maybe one you can solve, the other two they should solve. At 0 time, which is the time, I can choose the time 0 any time. I'm starting where I released it. At time 0, x equals 0. I did not give any displacement. It was here, but I hit it with something to give an initial velocity v0. They have to find out how to use it. Now, how do you plug in this one in this equation? At t0, I need to know v. How would you know velocity? First derivative. You just make it. Earlier you saw second derivative, right? I had taken the second derivative. You take the first derivative. That gives you the velocity. And plug v0 in there. At time 0, put time equals 0 here, x equals 0, and try to find some constants here. The third one is at t0, time 0, I pulled it, also hit it with a hammer to give a velocity v0, which could be up or down. Doesn't matter. Then try to find out a formula for maximum v. Ask them to do these things in the class if possible. Okay, good. So v, first derivative, this is how simple it is. A remains a, sine, derivation of sine, the derivative of sine is cosine, but this omega comes out, omega cosine, omega t plus v. This is the equation for velocity at any time. All right, so there, that's where they need to plug in this v0, and then a, omega, omega is square root km, cosine, omega t is 0, so plus phi from there. Most likely you can get the phi out. All right, check with the real numerical values for the mass spring. If you brought a mass and a spring, ask them to plug in those values, the value of the mass and the spring constant. Okay, and see if that matches with the calculation matches with the measured ones. That's going to be really exciting for them. How does t, time period, depend on the amplitude, mass, and stiffness? Does time period. Pull it even more and release it. Again, take the video and then ask them to calculate the time period. They say there is no effect of A. This depends only on spring constant M. Prove it to them using that video. Okay, it doesn't depend on that, but it does depend on mass and stiffness. K over M square root. If it is stiffer, this frequency and also that frequency gets higher. If the K goes up. If the mass is heavier, the frequency lowers. It slows down. Okay. Time period is opposite of that. So time period goes up if you increase the mass. Good. All these concepts have to be built in. Also, here I have created an Excel sheet, given all the data. Stiffness is that much, mass is that much, 100 grams, 15.79 Newton per meter. If I could pull the spring by 1 meter, it will have 15.79 Newton as force. But you don't pull the spring by 1 meter, right? This small spring, it will go into the plastic zone, get permanently deformed. Delta x, so delta force divided by delta x is k. It's the same thing, it's linear. That's our assumption. Mass, so they can calculate omega by square root of k over m. Calculate the frequency, omega divided by 2 pi. Time period, 1 over f. Amplitude is how much displacement you're giving. Let's say we're giving 5 centimeters, 0.05. At time 0, plug in the values, calculate the phi. This number is important. What is it? In terms of radian, what is it? Let them think about it. Okay, now I take the x formula for x, the displacement for various time, I calculate that one. Okay, then I plot it. Vary these parameters to see how this plot changes. Okay, ask them to do this in the class or as homework. Good. Homework 1. Assign this as homework. If the mass is released from a position where the spring was unstretched, this is a difficult one. I have the spring, I hang the mass, but do not let it drop. Just leave it there, hold it there. First, when you're doing the experiment, you had slowly lowered it down to a neutral position. Now I'm not releasing, bring it down. From that unstretched spring position, if I drop it, what happens? It will vibrate. What will be the amplitude? Verify with energy balance. Go beyond what you are teaching. Push them. Mass has potential energy here. When I release it, it tends to drop, but the spring is trying to pull it back. It will go down, but at some point it will stop and pull back. Okay, it will vibrate too. But let them do that on their own. Let them think about it. It had that much of energy. At some point, the entire energy, potential energy, if it drops by x, maximum drop, that has become has been converted into potential energy of this spring. What's the potential energy of spring? Half kx squared, because linearly varies, starts with 0. So area of a triangle. They should think about all that. Use the same mass and k data as above, but now the condition has changed. It's not starting from neutral position and pull to stretch. I drop it from wherever the spring was unstretched. It's different, slightly different. They should figure that out. Homework 2. Explain why for a simple pendulum the time period does not depend on the mass. Okay, simple pendulum. They have studied in physics, mass of the bob. But for mass spring system, it does. They should find out. They should think about it. Do you know why? Okay, think about it. Think. Do some research and answer the following in a few lines. While studying engineering vibrations, why do we study a mass spring system? How often do you see mass spring systems everywhere? Ask them that, but I'll tell you the answer. This mass spring system is the easiest thing to study, but very complex structures or systems can be modeled using many mass spring systems. Okay? All right. Once you have understood that, you can use the same principle to model very complex things too. Entire car, you can model it using some assumptions, some simplifications, so basically some masses and some springs. All right. Good. Vibrations. What else can we do in this while studying this vibration? How would you find K, spring constant of a spring? Ask the students. Some of them would know, others have to learn from you or from each other. I have a spring, I brought it there. I know that I brought a 200 or 100 grams mass, and I want to hang it, but I don't know the stiffness of this one. Okay, I'll give you a hint right away. Some of you are smart, probably know. Take a ruler. Okay, take a ruler, put it next to the spring. When you hang the spring, release it slowly, see the displacement of the spring. And from that displacement, you can find out mass divided by displacement. It's the spring constant. It's that simple. I'll not explain the details. Derive velocity and acceleration formulas as function. Velocity you already saw. How are you going to derive the formula for acceleration? Take the second derivative. Finished. Plot the velocity and acceleration on the same plot that you saw. I plotted displacement. Plot velocity and acceleration. In Excel, you can use Mathematica or some other tools if you like. Observe the plots. Okay, observe the plots and find minimum, maximum, and draw some conclusions. Did you see that? Here, where was the initial, all this maximum, where is that? Because I released it from 5 centimeter, and that's where it is. Here, x is shown in this direction. Actually, I have chosen x in that direction. Okay, so it's not starting from 0. It's starting from here because I have chosen this one as a reference, and initially I stretched it that. Let them think about it. They need time to think, because you already know these things. I'm speeding up, but they need time to think. And it's better for them to think and come up with these things than you telling them and they just memorize, okay, whatever the teacher is saying must be correct. That's not right. Plot the velocity acceleration, observe the plot, find the maximum and draw a conclusion. What is the phase difference between x, v, and a? When you plot on top of each other, they'll be surprised the peaks are not matching. Okay? When there is maximum displacement, velocity is 0. Acceleration is maximum, but when there is 0 displacement, velocity is the highest. So there's a phase difference. Explain to them. Okay, what is phase? What is phase? You take one sine curve, another sine or cosine curve. Suppose their frequency is the same, but they're shifted slightly. That part is the phase. That phi is the phase. Okay. In what other forms can the general solution be written? I chose sine, a sine omega t plus phi. You could have chosen cosine. Only thing that's different between sine and cosine is the phase. It's shifted by 90 degrees. That's it. They should know these things. There's a sine function. I can write the same thing as cosine function. You can even write a sine omega t plus b cosine omega t. That would be a solution too. Sine is a solution. Cosine is a solution. A linear combination would be a solution too. Okay. All right. They should understand these things. How mathematics, you can change a little bit in mathematics here and there. Basically means the same physical system. What are the potential energy, kinetic energy, and total energy of the system? Ask them to calculate. Okay, for the same sample, they can calculate using the symbols also, but numbers are always better. Okay, they should know that in that system, energy has been conserved. I'm not assuming that there's any damping, etc. So, potential energy of the mass and the kinetic energy of the mass is constantly being transferred into potential energy of the spring. Okay? All right. How does the total energy vary with amplitude and frequency? That's very important. They should understand from that formula, they should be able to calculate. Now they know the force, they know the velocity at any point, so they should be able to calculate potential and kinetic energy. Okay, and the total energy. And how does it vary with amplitude and frequency? You'll be surprised. Most people cannot find that out intuitively. They have to go through the mathematics to find out using simple formulas. Half mass times velocity squared is kinetic energy, etc. All right. Let them find out. How does it depend on the frequency and amplitude? Think. If you could derive the formula from energy conservation, it's possible probably. Go beyond what you are teaching, what's written in the textbook. Probably they'll learn that in the 10th chapter, but still get them some hints. Is it possible? Sure, it's possible. Okay. What if you have two masses connected in series? Okay. One spring, then a mass, and from that mass there's another hook, another spring, another mass. Very similar approach, one can find the solution to that. Okay, how would you formulate and solve the problem? You write down, you'll draw the free body diagram for each of these. You'll assume some displacement here, some displacement there. Okay, x1 and x2 maybe, and then write down the equation of motion exactly the same way for each of those. Then try to solve two equations. Okay, introduce degrees of freedom and modes, probably in the next lesson. Introduce what's degrees of freedom and modes. Vibration and sound waves are related. They should know if something's vibrating, if there's some medium nearby, air or water or something like that, it's going to cause waves in that medium and that becomes sound. That's it. Or internally in the same vibrating system, there may be sound traveling. Suppose there's a long beam and one part is vibrating, that wave will travel the sound to the other end. Okay, they should know these things. They are related. Similar studies are used in electrical engineering too. It's not only mechanical vibration. You get very similar equations in electrical engineering too, and AC circuits. So you'll get the similar solutions also, similar phenomena. It's not going to be mechanical vibration, but maybe flow of electricity. They should know that what they are learning here is going to be useful in electrical engineering too. Good. That's all for now for this lecture. In the second lecture, we'll see some more examples, slightly more complex things, and some nice pictures too. Thank you very much.